other companies. It makes sense to learn VHDL, friends, because VHDL very widely used. It is also very widely used in Europe. Only America, not everywhere in America. I talked to one American like this. He told me, for example, they use it a lot in East Coast. I mean, they use it on the East Side. America, I don't know many details, but now I will tell you. I'm going to show some of the trends. For example, this Siemens from his site, it's like this. So as design language, by the way, if you are already doing validation, if you are a verifier,
there are actually two alternatives. If you are a verifier, Verilog. Verilog as a verification language is actually going away. The system stays Verilog because
SystemVerilog for validation. So a lot of the features of this validation, I'll go over it. It's in the slide. It's in the other tabs that I've got. Many features are already embedded,
is built into the SystemVerilog language. So if you are a verifier, you are already using SystemVerilog. So I think the rate of verifiers using something other than SystemVerilog is low. But how do they use it?
When do they use it? Now let's finish the verifier part first. If you are a verifier, actually, I think you have two alternatives, SystemVerilog or VHDL, which you don't have. Verilog, because I'm Verilog. There's free verification libraries. I don't know. Maybe there is, I don't know. If you are a verifier, from my point of view, you need to use SystemVerilog. Much, much better. But let's say you're a verifier and you're a startup, or you don't have enough licenses in your company. Because, for example, let me give an example from Turkey or Europe. The designs are usually in VHDL, and you can actually use recommended in all guideline.
You will use the SystemVerilog recommended by the verification gurus, recommended in the universal verification methodology. You with VHDL.
Let's call these two designs VHDL at the same time. And you do the verification with SystemVerilog. As soon as you use it in Quest.sim, ModelSim, then in Active HDL and such tools, simulators, these tools already detect that it is a mixed license at the same time. Because one of them, VHDL, here you go, HDL part, hardware description language. In the last CV review, a friend wrote something, for example, he wrote VHDL language. Pay attention to such things. After all, this is the language at the end.
So don't write language afterwards. It shows that you know what it means.
And the V should come from very high-speed integrated circuit. Let's look at it now. Because there are so many things, I'll do it like this right now. So let's not waste time with him now. So V stands for very high-speed integrated circuit. In HDL, wait a minute, which one am I? I was on that Siemens slide. HDL stands for hardware description language. That's what VHDL stands for. Verilog, Verilog. It is already direct open form. The system is actually in Verilog. On top of that, some such validation functions are embedded, and object-oriented mechanisms are already given OXI-based. One, to see. That looks like hardware description language, HDL. The system becomes object-oriented in Verilog. Think of it like this. Think of the C language in software as C++. So object-oriented, here come the features. But, and on top of that, there are concepts that I will talk about in a moment to verify such a very nice way, verification concepts. Their functions also come embedded in the SystemVerilog.
Now you can also verify with VHDL because it is a mixed language and these simulators are very expensive.
There is a trend about that too. But when you verify with VHDL, there are actually two of the biggest verification
infrastructure.
There are. One is OSVVM, open source VHDL verification methodology. The other one is UVVM, that is universal VHDL verification methodology. Since they are based on VHDL, for example, you work in a big company in the defense industry, but Quest.sim's mixed language license, there's not much. It's just that hardcore verifiers use it. In that case, you use VHDL. Based on this open source from GitHub, the latest version of UVVM or OSVVM, download and use them. You can just verify using a VHDL license in normal ModelSim or Questa license, but of course, you can do it at a certain level. So functional coverage is the verification I'm talking about. Because according to the system data, so the system, most of these VHDL's free verification
according to their mechanisms, I mean, their methodologies, I'm talking about OSVVM and UVVM, much more
skilled. You do most things much faster. So, I mean, both can be used like this, actually. You know, not necessarily for verification. There is no such thing that you will use the system data. It is yours, the number of licenses of your company, how much, depending on whether he has good economic power or not. So it changes. Now here, for example, design language adaptation next 12 months. He did something like this. Look here, for example, SystemVerilog is rising because SystemVerilog is now also used for design. So tools, that's why Quartus, his Vivado, whatever Phoenix's tool is, then Microchip's tool in the same way. Did the Liberoid change at some point? I don't know afterwards because it was very Liberoid, then maybe it changed.
Their SystemVerilog support for design is increasing. We are currently looking at design language adaptation. I mean,
that's probably it. I don't know if there's like, they did it in 2018. When we look at trends, for example, there is verification language adaptation section. Here's the system data C thing. Verification, they used the VHD, 2012, but then it went down. Here's what I'm guessing. In verification language adaptation, they use either UVVVM or OSVVM. So this is more for medium and low budget companies or for startups. It makes much more sense to do it with VHDs. Verification, because licenses are very expensive. I mean, a mixed language questioning license is like 50 or 60,000 euros. For Verilog, I mean, they also use Verilog, for example. So in verification language, look at Verilog. They somehow confirm it. So they write the functions themselves, or they're writing, I mean, for example, CocoaTB or something like that. I don't know that Verilog-based CocoaTB.
Now, there is a lot of content. Let's not go into CocoaTB. It is also such a verification methodology. Again, there are other things. Let me tell you what I know.
If I don't know what I don't know, let my friends share the links from there, either from Discord or from YouTube's live broadcast.
Now, Orhan was saying something, let me say it right away. We have no chance to program with Vivado, because this is FNX. In Vivado, you can only program Darling's FPGs, so you cannot program FNX with Vivado.
That's the way it should be. I've never used FNX.
But Vivado only supports Darling's FPGs. I've never used any other brand of FPGA.
I didn't program it with Vivado. The programming part is already a JTAG interface. That's not the point. The point is the design and the design analysis. The design is called compilation. Then after that, placement, first from your hardware description language, is transferred to the gate level. It is transferred to the gates with the synthesis left. Then in that gate level design is now transferred directly to the resources of that FPG. So what we call placement and routing, which we call placement and routing. And after this placement and routing, you can do timing analysis, and then there you go. Minimum by reaching maximum frequency while consuming resources. You need to complete this design, ideally. But of course, you need,
according to your wishes, your team leader either...
And in the requirements document, it says, use this much resource, use this much of the FPG, use 10% of this model FPG, use this many registers, and so on. Those requirements are usually clear. If not, after you make the design, you should report to your team leader that you have used this much. You need to get it approved.
Minimizing resource consumption in the job, the frequency must also be maximized. And again, I mean, you can't do, for example, 5%. You can't do 5%.
You can't run it at 500 megahertz because very optimized designs like this can run at 500, 600 megahertz, especially in your speed grade mod. So if your slow FPG is not very expensive, this is what you're going to get. The limit used to be 100. Now it's in the 200s. They're 250s. You know, even complex algorithms that are now running at 250, 300 megahertz. Because FPGs, because of this Moore's law, nanometers are shrinking. Now 7 nanometers, 5 nanometers of these transistors. Size. Here's ASML, the company I work for. This makes the lithography machine much more precise. It's much more precise.
Oh, yeah, the chips are made much more precisely. Here we go.
Going Apple, Siemens, Apple, Intel, then AMD, that followed by the purchase of,
is buying, making its own chips.
So it's actually on top of the whole, on top of the FPG thing. And the companies that make the lithography machines, the companies that manufacture, that make the lithography machines. So without them, because they don't really make their own lithography machines, because they are very complex devices. Now that we've answered that question, so again, we'll take a look at that FMX, any other brand, FPGs. I mean, we used to have, by the way, let me tell you, for example, you could do this.
You write the opcode,
this design phase, which we talked about in the first 2 lessons.
Now that after you've written your hardware description language, VHDL Verilog or SystemVerilog,
then that code you wrote to gate level translation can be done with any standalone tool. You don't necessarily have to do it with in Vivado, in Quartus, or whatever FMX's tool is called, or you don't have to do it in Libero. The thing happens. Already the gate level is translated into a transfer file. In the old days, for example, a long time ago, when I first started, the engineers who worked before me, back then, there was a tool called Leonardo, for example. Leonardo,
this Xilinx is at that time, in the oldest ISE like this, it's like 4.2 or something. It's pretty old now. The last time ISE had 4 dots.
I froze at 7 or something, and then Xilinx switched to Vivado. Then Xilinx was bought by AMD, so there's AMD Xilinx. It's going through, in the earliest versions of SML, one called Leonardo. Here's the scintillation tool. And you would open it with your HDL code, compile it, synthesize it in the output of the synthesis file from Leonardo. Importing it into Vivado. Oh, I said Vivado, sorry. There was no Vivado then, import to ISE. And then placement and routing the thing itself. He was doing what it's called, ISE was doing it itself. This is Xilinx's IDE at the time. Program. I mean, after that, but as this technology advances, companies started making their own synthesizers. So the hardware description language
themselves to gate level, and then from gate level,
they used to be able to directly to their own FPGA technology, a technology at each gate. From level, there's a placement to the FPGA's resources. That's its how many inputs, lookup table technology. Here's how many slices it has an element. How many inputs and outputs, how many registers, how many multiplexer. If you have, according to your code, after the gate level, at the gate level, it turns it into ands, O's, etc. to the usual gates, not at first, and then it takes that, maps it from its technology. We can call it a technology map. At first, then placement, then there's routing, and then there's routing, routes those connections between the slices, from the slices to the RAM, the memory units. It's going, that's why it's called PNR, placement and routing. And then after it's all over, of course, you're going to have to count them as BJS and share to operate at the maximum frequency. The tool has to do, as input, as requirements, you say these things in the constant dots. If it can do it accordingly, without giving you any error, it does this placement and routing, after that placement and routing, and then you can either convert the file into the bit file, or here, the soft file, this soft file, we always call it soft. Each thing has its own standard bit file, soft file. These are direct FPGA programming files. It converts them into, and then you have to, usually an external flash, it's happening, this with digital cards, because after booting up, they're just going to pull this file and upload it to another file format, so they can upload it to that flash filter, you convert it to another file format. Like, for example, for years it was MCS file for Xilinx bit file into an MCS file. And the MCS file, when you power up the board, that flash stands up, it gets a little cloudy. The code running, going through the flash, pulling the interesting thing, pulls the file, uploads it, and it becomes the cloud. And then on top of that, socks and stuff like that. Now their complexity has become more differentiated. In the future lessons, I'll tell you. Now, how long we've been 1940, and you have 2040. So one important parts of what happened here, for example, for the verification methods, C++ was already used very little, hasn't changed much. SystemVerilog, the trend has increased.
Already, the number one, and it's not so new, This 2018, the pandemic doesn't even exist yet, so.
SystemVerilog is getting, rising in the verification part. So the verification language, as there is something else here, something critical. Let's see what the use of assertions. So these SystemVerilog assertions here. So VHDL, for example, assertions in VHDL, but yeah, very limited. The assertions in the SystemVerilog give you a very nice resolution, and very good information. So you can see that the design for functional coverage, this functional coverage, code coverage concepts, and here are their properties to what benefits you. Actually, these are here's what the simulator gives you. The bottom structures, code coverage system, code coverage CC and FC, and we'll cover them in future lessons. Again, as a lesson, I'll tell you. Now here and now, let's close this. One of them left. Now here, for example, he gave an example. Look, let's start with one thing first. We've already said for verification, SystemVerilog, because SystemVerilog is okay, and it's going up for design, but yet tools like this don't give you 100%. SystemVerilog is not for design. SystemVerilog to the SystemVerilog compatibility, and in Turkey and in Europe, still 99% of designs like this, I think 99% or something. VHDL is still, so for design anyway. Let's switch to SystemVerilog right now. We're going to take a look at. Let's look at Verilog or VHDL. I mean, that's a very, asked
people. I mean, for example, again, I'd like to see an American who likes VHDL more.
An American I talked to, which is normally the trend, in the world, in Europe and Turkey. VHDL is very.
In America, it was like Verilog a lot like this, say 10, 15 years ago. Then there was a group like that in America, and now they started to go back to VHDL. That's OSVIM. I'm talking about the one for design. OSVVMs here. Oh, chair.
Generalist. You can follow him on LinkedIn. The guy, he's a pretty solid guy. He's already on IEEE's VHDL chair. He's also OSVVMs, open source VHDL verification methodology. Here, the constant man thing, making sustains them, training them, and then his sharing updates as he makes them. He shares his new releases on LinkedIn and stuff. But for example, even though he's in America, for both for your design, both for design and for verification, the VHDL is enough. He says, which I call for your build. I agree with him, but verification for systems. If you start using systems like this, there's an incredible difference between you'll see that difference. But read the stuff. That's what I recommend. For example,
Jim Levis has articles like this, like that, very
not official stuff, but he's put PDFs like this on their website and stuff that he's working with. Synthworks Mini at a company like that, at a company like right now, he's saying like why VHDL is enough for everything. It says there's no need to learn object. The system is given their own keyword, like this, some key functions. There's I'll tell you in a moment on the other pages. We already do them in VHDL. The guy, but for example, then you're the one I work with, the team that I work with, definitely don't want OSVVM and UVVM. It's a little bit where you're going to validate, where you're going to design. They know that SystemVerilog is very more effective. They direct to the verifiers that use SystemVerilog. They say so that's the general trend. As I said before, the verification is SystemVerilog, but if it's design, VHDL.
I was going over I'm going to say, this is not Jim Levis, but that I met at a conference in America, another one like that, in his 50s or something, a very nice guru man.
I can't think of his name right now. But and what he said to me, for example, he says that learning Verilog much simpler, that I should start by learning both. He started, and now we'll get to the reasons, that both of these things in the sequel, learning Verilog, because it's based on C. If you know C like that somewhere, if you've learned Python, she's saying, for example, young people right now, most of them know Python, new graduates or graduates of a year or two, Verilog, because it's easy to learn Verilog. On top of Verilog, and on top of that, if you already know Python and object orientation, then the system is Verilog. You can learn it very quickly, but it's a bit more in the world trend. Verification Pete, just like verification Pete. Yeah, so we start with Verilog. Verilog, for example, you can learn Verilog directly, whether you're in Turkey, even if you are in Europe. Then you move on to SystemVerilog, but you become a verifier. Then what if, for example, there are those who are very much in favor of me, for example. I'm moving from design to verification right now, because there's a lot of
that I've learned designing in VHDL,
that I'm doing things quite differently, to explore a little bit, to explore this world of verification.
I myself, for example, with VHDL,
using OSVVM and UVVM,
I used VHDL, this universal VHDL verification methodology, and the open source VHDL verification methodology.
And then there's, when the system uses Verilog, there's something so much faster. That's how
you become capable. The other way around, because
they're all free for things that VHDL, UVVM, OSVVM, the publications. So in fact, these guys, the system is already embedded in Verilog, which is SOE right here, a standard written and published, created a language, SystemVerilog, derived from Verilog. SystemVerilog has minified. They actually minify with VHDL in OSVVM and UVVM, but I don't think it's effective. So what I'm talking about, worked in verification or verification. VHDL gurus. There's one in our team who has been designing VHDL, and they always say then for verification, SystemVerilog for design, VHDL for design. But you've already, from the very beginning, verification suite, if you have it in your head, because that's a very valuable job. by the way, verificationists. There are far fewer verificationists in the world, so there's a great need for verification. For example, I'm a SML from VHDL designer at work, SystemVerilog, verification to SystemVerilog verifier. One of the reasons it was so easy.
The need, because SystemVerilog, who knows UVM? Very few in the world. There is, so according to, for those who know VHDL or Verilog, then designers, verifiers are much less. Right now, for example, in our projects, we have a direct
verifiers now. There is a shortage of verifiers. Not enough verifiers now because they can't keep up and verifying. And it's pretty much by design. I think it's even more difficult, more labor, and it's more of a whole. I mean, you do the thing, the designer designs it, and you try to find the bugs in it. Yeah, you have to look everywhere. There are a lot of concepts, verification concept. So, from the very beginning, for example, start with Verilog, learn SystemVerilog, or learn SystemVerilog directly. You can also go to the verification path. So, if you're an FPGA guy, if you like FPGA stuff, and I think that part is also very enjoyable. For example, he's done something here, the same code, a similar code. Let's see. Yeah, this is how I saw it. I bought it. I didn't analyze it in detail, but it shows here on the left here. There's an archetype of VHDL. You'll learn these keywords already. You will learn. I'm going to show you here. Here's what a component is. Here's what a process is. But I will recommend trainings. So I'm already suggesting you come to the Discord channel where there are free trainings, paid trainings. I recommend now that they've got the money. So if you're in a startup, you can ask the owner of the company. If you're in a big company and you know the team there, you can ask your manager. You can try to get. So now, like I said, I'm a Verilog. I started with VHDL in the beginning. In 2009, I was directly in the internship. VHDL, I learned, then we learned half of the internship, and then we went straight into coding. So actually, since the summer of 2009, I've always used VHDL. It's always been FPC. But I like VHDL. It reminds me of, it sounds readable. So some now, for example, here, explained it in writing. We need these. No, we can go here. Let's move to the other sides. So I think the biggest beauty of VHDL is it's called strongly typed. So if it's like Vlog is not strongly typed language, it's not. See, this could actually be like a little note. And here's what happens. Strongly typed. I don't want to read the English now. After all, it's in Turkish. We're doing it in Turkish class. But strongly typed. Actually, the language will not let you. For example, you can connect ports or signals to each other. While connecting hierarchically, when you're making the connections, I've got you guys
forcing you to follow these rules.
And he said something like very quickly in English. Let me read. Strongly typed. When an idea that describes the informants of very strictly on mixing different data types and values. So you can't mix things. For example, in VHDL, I'm going to go two signals of different types.
Two signals of different types. You can't directly connect them together.
For example, this is an important feature of a strongly typed. And in VHDL, for example, there are a few, by the way, those tutorials are already VHDL. So, or Verilog tutorials, they'll show you a direct comparison. They will show you a situation like this is happening, input ports in VHDL. You can't do anything. You can't leave them empty. For example, usually STD logic vector, standard logic vector, or also standard logic is defined. So bibitse STD logic ports, and if multi-bit, the STD logic vector is defined. So it's like this, the one in the example you see here, and this one here, bibitse, usually 0 down to 0 is not done. It's straight STD logic. Put a semicolon here, input like this. This is one of the important features of VHDL. So most people, for example, realize it later. And I realized it later, in the first 3 or 5 years or something. So I didn't know in VHDL, as soon as you don't connect the inputs, compiler error. When you give, for example, in Verilog, since there is no strong type, so I don't want to make you, according to the rules, that it doesn't do anything because it's not guided. So you don't have to follow too many rules. I would say it's more of a relaxed language. So if I had to put it like this, if you don't connect the input ports with VHDL, it's going to throw an error, which I think is a good.
And then you then do. So at the next higher hierarchy,
you connect that signal. Here you connect the signal. You define that signal as constant there, M-man. But in Verilog, you can't connect it directly. Then if there are default values, here's the input port. You can automatically. He's taking. Verilog is more relaxed, more of a comfortable language according to VHDL. These are. Because FPGAs are expensive, so the systems that they're used in, because they're expensive, military systems, or I don't know, it's very, because it's used in expensive products and stuff, because FPGA, it's not exactly a solution, it's a cheap solution. It's not, usually FPGA very high like this, an algorithm to implement a complex algorithm, parallel processing capability, too many input-output ports, because the FPGA is to utilize them to the maximum like this, to utilize them to the maximum to go and, I don't need
to a low-cost design,
If you put the FPGA, you raise the price, the price goes up, the price of the product increases, he did over-design, you'd be, the FPGA thing is a bit more, as it gets more complex. The parallel processing is like this, as timing becomes critical, like this, the nanoseconds, 10 nanoseconds, 100 nanoseconds, where latencies are important. So what did he say now? Your HDL model is capacity abstraction. Level is a little bit like at the gate level system. At level, how did it happen? Let me tell you something, by the way. Verilog is used more in AZ. I know. In AZ designs, they use Verilog more, or its completions in low-level modeling. For example, to see low-level in modeling, Verilog is better than VHDL. And again, I've saved these recorded under this lecture. I'll share them with you. You can read in detail. Now let's not go on.
But let's go over some other things. Let's go over. So here, for example, without making a very nice visual.
Without making a very beautiful visual, and here, I'm shutting down SystemVerilog versus SystemVerilog here. What are the differences between them? So I've explained this a little bit. Again, I'll send this. Or look, there's a lot of writing here, for example. So, what's in Verilog, what's in SystemVerilog, but it's not very important because it's already Verilog, something like father of, like Messi's father. No, but Messi's father doesn't play soccer very well.
But the system is Verilog, mate. So think of it as Messi. He got an upgrade from that.
After that, because on top of that, there's a lot of new, procedural blocks. Always comp, always FF, always latch. They've embedded a lot of extra ready-made functions and so on. A very capable language. Gave key differences. Verilog, SystemVerilog, which is good again. VHDL, what's in VHDL versus Verilog. Then let's take a quick look. User-defined data types are not supported in Verilog. He says in VHDL, yes, you can define a data type yourself and use it. There are enumerated types and stuff like that. You'll see them as you get the training. User-defined data types is not in Verilog. And I also mentioned strong language is employed in VHDL, in Verilog, weakly typed language, with data types like bit, vector, wire, reg, onsite, sign, integer.
Real? What did he say? Strings is.
Well, what about these things like similar things? And it also connects them. It doesn't give an error or anything. But that's a little bit.
In these expensive systems, these expensive FPGAs, you can make mistakes, implementing the wrong things,
and implement the wrong things. For example, in the defense industry, I've never seen a Verilog design.
In the defense industry, more where it's used.
Tools that work sometimes by codes themselves, IPs, generate to be able to read some of the for the code that it generates. Because you can, for example, from Quartus or Vivado.
Here's my design, but this project of mine, the VH, even some files, you find yourself producing Verilog again. So such low level
to the files after that, because in the design, the tool it's based on C++, I guess. So these things, they're programs, Quartus, Vivado, etc., more inclined to Verilog. Even though you choose VH, it still produces Verilog. So that's why it's good that you know Verilog, at some level. That's useful. All sorts of, but for design, I'm in favor of VHDL, and most people are in favor of VHDL. What I've seen, no one's ever said to me, I design in Verilog. It's much better.
But it's more useful.
But in verification, that's where knowing Verilog and going from there to verification. There's a benefit to that in terms of the system Verilog.
What it says.
The written integer equivalence is supported by SystemVerilog. He said something that corresponds to it. Is there anything very critical? Because there are other paintings. I want to continue. I'll throw these out again, and you can examine them in detail. For example, look at one, the same code this time, the same look, let if, else if, okay. On the left, he did it in VHDL. On the right with Verilog.
It's not so much like,
Look, but I'll tell you this. For example, in both in VHDL and Verilog, if you make a latch like this, here, for example, it's not a clock. A clock is not an element. The latch is actually the flip-flop. Not edge sensitive. It's level sensitive, what we call a latch. Then the input signals, not the edge, but the level of the trick. He's getting...
Let me put it this way. Wait a minute. Did I say something wrong? Let me think. Things.
Registers, flip-flops. Clown rising edge, or is on the clown edge an operation? Well, latches. Latches don't connect directly. clock is not connected directly to the latches. See here in both of them, latch implemented already, of these signals, these input signals that it connects, depending on whether they're 1 or 0. The latches does something like this in the ASIC or something. These latches, they use in VHDL, not latches, 99% flip-flops, 99% flip-flops. But I didn't say in VHDL, sorry, I'm in non-ASIC designs. So, you know, ASICs are now for mass production. For mass production, and they stay that way. They're like this, detailed timing analysis and so on. Much more. The verifications and so on are much more. It's being done. So, for example, we can put an analogy. Maybe because of these ASIC guys, obviously he's using. It could be just that we educated guess. So it's not, because I didn't design ASICs that much lower level. For example, SystemVerilog, such a new language. It's not. They're doing it in Verilog with Verilog. Then this C-based SystemVerilog transition to C++, like from Verilog to SystemVerilog, transition and verification is much better. Maybe that's why they use Verilog. They're using Verilog, so it could be in the design that they're using Verilog. I'm talking about, so for example, SystemVerilog came up, much more capable, messy now. I told you the language. So for example, in SystemVerilog now, you can type always here in this sensitivity list, the signals in this sensitivity list, or like this. You don't have to write in VHDL, Gene, what we call the sensitivity list. The sensitivity list is actually when one of the signals here changes. This process is activated. The assignments here. This if-else statement starts working. In SystemVerilog, for example, always there was an example here. Immediately, let's come always latch, for example, always combinatorial logic, or always latch on this, for example. Yeah, you don't need to write here's enable 1, enable 2, enable 3, a 1, a 2, a 3. These are the signals that are in there. The signals that are used. Normally these are so that's the
read, but you put always latch the assigned signals. It automatically throws the assigned signals, like, that you can write much faster.
You can write, for example, SystemVerilog. If you're writing, so there are fundamental differences like that. Let's move on. Let's try to finish these remaining in our 15-20 minutes, and then we'll do a question and answer session. Again, things in the meantime, feel free, guys. If there's something you don't understand, you can ask the guys on Discord. Right now on the Discord, 3, 4, 5 guys on Discord right now. Of course. Ask him. Or, for example, I see. He'll fix it later. I don't see his name, for example. This is the friend you added. But he'll write it down. What do you call it? And put his name on the Discord. We'll give him access to all the groups. He can ask him to do his thing on Discord to unmute. I'm waiting for him to ask the question. So he can ask at the end how. If you want, here's a beautiful painting. For example, I'm waiting. If he opens it, I'll answer the question. Here, for example, he did it well. Verilog VHDL. See, comparing two design languages. Two hardware. Hardware description language or hardware description start. See, Verilog ASIC designs says on a VHDL FPGA designs. He said when it comes to ASIC, application specific, integrated circuit. That's ASIC, and these are usually factory packaged. For example, if you're using, if you use Apple's SOC, for example, 5 nanometer most of the technology. I don't know if they've gotten it down to 3, 5 nanometers, and it can go to very high speeds. So many different capabilities.
Or Samsung's chips, or their own.
The chips, memories, and so on and so forth are ASIC design. So actually, in the ASIC world, you design everything that's made with transistors. You're designing memories. It's okay here. That other application specific is actually application special. The integrated circuit. A Verilog ASIC designer said weakly type, strongly type. This we told you another job like this, prescriptive network, STD logic. You're throwing STD logic. You can't leave the input ports open like this. You can, in Verilog, if there is a default layer, it happens automatically. It happens more like this. Well, this low verbosity, high verbosity, what he calls actually in the simulator and so on, as the code flows in the simulator. For example, your design, high verbosity. Here are these assertions. Using these assertions, because VHDL also has assertions. I don't know to what extent in Verilog, low verbosity there. It says that's assertions also, levels of assertions. There's warning after that, error, fatal. When you say fatal, it looks cracked, for example. A simulator, it just gives a grade, it prints a note. That too, so guide, our simulation, you see guide, that you write next to it, like warning, your text. And then after that bit, so for example, it says, oh, warning. And then after that, here, blah, 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 this output does not match, or it says, for example, this output is expected to be a hexadecimal FC, for example. I don't know, but this is the result. Here's the result, for example, hexadecimal 50. It came out. So that's how your own internal signals, the values inside my crossbow, the values, you can suppress the value that you read. In the simulation, ideally, it's printing it in the guide is also an option, but they usually do it in batch mode or in command line mode without ever opening the tool. And they say something you don't expect, self-checking. I'm talking about the concept of the kex pen, and the unlucky ones are spilling out of the thing. There's your windows over there, but where's my command line? For example, there's, let me open this PowerShell, for example. Here, for example, when I run the thing, if there's no problem, it's like, here it is. That simulation could be its tickle, or the simulation. Here, he might have a file if there's nothing. He's waiting here. But when something comes in, he presses. Then, without ever opening the tool, you can see where the problem is, where there are problems. But to analyze in detail, if you want to drill down from waveform, you can go back and see nanoseconds. It says, yeah, so you can have them printed. They should be printing them automatically anyway. The simulators, at what nanosecond, at which picosecond, at what nanosecond, according to sensitivity. So you don't need to open waveform. Let me put it this way. You don't have to open waveform. And then you do the analysis, and then you do the review. I've seen this a lot. For example, an engineer of 10 years running the simulation like this, opens up waveform, trying to solve bugs in waveform. And the reason is the test he did, that he wrote the test for me, it certainly wasn't written by a verificationist. If the verificationist wrote, he would have gotten a direct result. That's how he's in waveform. He wouldn't try to solve the bug. He solves the issue first.
I see, for example, for 3 days, I've seen people looking at waveform, for example. My friend,